Thank you, class, for showing back up. This is going to be week 3 of Introduction to Antenna Basics. And this week is an introduction to wire and traveling wave antenna design. And I'll get into what that is here in a bit. So some quick housekeeping items that I wanted to mention. Last class, there was a live question about testing antennas without connectors. And I apologize, I think I didn't fully understand the question, and that can happen sometimes. Being live, not always getting the point across and trying to help y'all in the best way possible. I realized after the class, I think the person was asking about those little bits of wire antennas that are just directly on a board. If you are wanting to test a little wire antenna that does not have a connector already attached to it, you would do that by soldering it to a connector, right? And in one of the YouTube videos that I linked to, it showed the person on the YouTube video doing that with showing a paper clip, right? So you do have to attach it to a connector somehow to do network analyzer measurements. That's how people have gotten around it before, but that would mean that you would have to take it off of the board. So apologize, I hope that's a better answer. And I wanted to link to an open source FEM software that I heard about called Elmer. One of my friends just attended one of their live webinars, and unfortunately, I think they're done with webinars until the fall. But it looked like they had a lot of resources available if anyone was interested. I think the last webinar, and they've posted the slides, and I think they post the recordings of everything that they've done was over microwave component design, if that's of interest to anyone. And I haven't used it at all. I just found it and thought I would pass it along because I know people are always interested. So recap from last class, we talked about testing. So some important items to remember, particularly for the final quiz at the end of the class. Return loss, or S11, is the ratio of reflected power to incident power. VSWR, or voltage standing wave ratio, ranges from 1 to infinity, positive infinity. It cannot be 0. A short circuit is 0 impedance, and an open circuit is infinite impedance. And you should ideally know where short, open, and load is on a Smith chart, such as shown on the right. And going from left to right on the Smith chart, you have your short, your impedance match point, and your open circuit. So this class, I'm going to talk about dipoles, monopoles, Yagis, very quick hit over Baluns. I'm not going to go over them in depth. And then helixes, or helical antennas. And I apologize, I don't actually practice my classes or rehearse in any way. So I have more slides than previous classes. I think we'll be able to get everything in time, but if not, I can stay a little longer for the Q&A. Quick note, very important before we begin. So we're getting into actual design here in this class, recommending exactly what you need to do with calculations and actual links and how to make it. And if you go out from this class and you say, Karen said to make this wire 0.96 times 1/2 of my wavelength, and it doesn't work, the resonant point is somewhere else, Karen is an idiot. Well, that might be true actually, but the point that I'm getting to is that you need to tune your antennas. There are so many variables with what goes on when we construct an antenna, right? Your impedance might be a little off. It might be your test environment. It might be how high you have it off your ground plane. It might be stuff in your environment having reflections. There's all kinds of stuff that you might need to do. All antennas need to be tuned from the recommendations that are in the books, right? And the next point that is misspelled is that you need to prototype long and then trim in small increments, right? So if you are using copper wire to construct a half-wave dipole, cut it a little long, take a measurement, and then trim bit by bit. And this isn't just an amateur thing or for students, even professionals in the workforce, when they're printing their own boards in-house, have to tune their antennas because of everything. And that's even with amazing modelers like HFSS, right? You still have to tune a little bit when you're in real life. So please don't think that you have failed as an engineer if your first go around it is not perfectly resonant where you wanted it to be. And I'll even show some examples towards the end of the slides where you can see what happened when I didn't tune, because I was a student who left everything to the last minute, which is certainly not what I do anymore. So let's get into it. First, I'd like to talk about a half-wave dipole, right? 1/2 of a wavelength. Now, typically these kinds of antennas, they're going to be lower in gain, 2.15 dBi. Remember, that's decibels relative to an isotropic radiator. And they're going to be an omnidirectional radiation pattern, kind of like a donut, and I'll show a picture of that here in a minute. And they're linearly polarized, right? When that E field vector is operating either like straight up and down, or if you have it placed horizontally, straight across like that, right? Linearly polarized. And one thing you want to be careful if you have just a straight half-wave dipole is that points of maximum voltage that you can see here on this GIF, they're at the ends of the antenna, right? That's where the highest voltage is. So we don't want to be hanging on to that with our hands, right? And you don't want to have it to where children can just walk up and touch the ends of those lines. So you want to take care that you are operating safely. And remember in my previous example where I talked about prescriptive calculations, right? Due to the operation of the wave on the dipole length, it's not a true exact 0.5000 length of half of your wavelength, right? It's a little bit less. 0.96 to 0.98 is about where you're going to have it. So that's one of those things where you're going to design long and then trim down, right? Another thing that you're going to see when we're talking about antenna designs is different antennas have different input impedance. And remember, we talked about in last class the importance of impedance matching, right? So whatever line is connected to your antenna, we want that to be matched to the input impedance of the antenna. And this can vary depending on what you're doing. A lot of what we'll be talking about today it works well with coax lines because of the lower frequencies. You typically would use, waveguide to connect to higher frequency, and there's some other stuff. But the impedance for a half-wave dipole in free space, in perfect free space, is 73 ohms. So you can generally use 70 ohm coax and expect a pretty decent match there. Now, my next point says impedance depends on many factors, right? And I mentioned this when I talked about tuning. It might be different depending on how exactly your antenna is constructed, right? And so that means that if 10 people build their own versions of a half-wave dipole antenna, their exact impedance is all going to be a little bit different, right? Because no one's going to be operating in that perfect free space environment. So that's something to keep in mind, again, when we're talking about impedance matching and tuning, right? There's going to be some work to be done there. The other thing that's important to mention when we talk about dipoles is that they're a balanced antenna, right? If you can see the GIF on the right, We have our voltage source there at the bottom, and we have our current going in and going out, right? In and out. So that's balanced. And so when you connect it to something that is unbalanced, such as a piece of coax that just has one direction, you have to take steps to match that, right? And we'll talk about how you do that towards the end of the slides. But just to make sure that I've gone over the representation here, remember this is all alternating voltage and current, right? And I mentioned the points of voltage being highest there at the ends of the dipole, again, approximately half wave here shown. And you can see that alternating current is what radiates that wave out. Here, move my hand so it's a little bit better. And that's where our electric field vector comes, right? So when you have your polarization, it's going to match the orientation of that dipole, the orientation of how that current is moving along that dipole. So if you have it oriented this way, you have your current going back and forth, and you have your electric field vector going out there. So just remember for polarization, that it's going to match the orientation of your dipole, right? So that's important both when testing, but also transmitting, receiving whatever signal you're communicating with. And I like this as well because it shows that electric field vector that I was trying to show poorly with my hands, right? But you can see here, this is where that polarization comes from. This is where that electric field propagates from, is that alternating current in the line. So I did a very quick, or attempted a very quick simulation with that new CNOS antenna design software that I posted in the class. And the units here are in millimeters. And so I could not get the hints to go away. I'm sorry. I clicked hide them multiple times, but they wouldn't go away. So you'll have helpful hints unless you're just better than me at hiding them. But this is from one of the standard templates that the software has available for you. They have a dipole, right? And so you enter 3 parameters: your length, which is going to be that approximate half of your wavelength for whatever frequency that you're going for. Your feed gap size, you want that to be small as possible. And you can see here, I have a length of 15 millimeters and a feed gap size of 5 millimeters. That's huge compared to the length of it. The 5 millimeter gap size was a variable that was already in there that I didn't change. I would not recommend in real life actually using a 5 millimeter gap size with that length of antenna, right? And then your wire diameter, how big is the diameter of what you're working with? Are you working with, just more slender copper, or, big piece of aluminum? And you can vary your mesh options from looser to tighter. Tighter meshes or more extensive mesh is always going to give you a better result, but it's going to take longer and drain more resources on your computer. And this is the kind of radiation pattern that you get from a dipole. And you can see here what I talked about, the ratio of the 5 millimeter gap size to a 15 millimeter half wave. You can see how big a chunk that looks like and why that is not a good idea to actually do in real life. But the radiation pattern on the left, you can see for directivity that's plotted here, it's about 2.4 dB. And you can see it's that donut pattern, that omnidirectional pattern that goes around the dipole. And one thing that I do really like about any software that plots a radiation pattern, I'm a very visual learner. I had a very hard time trying to teach myself polarization and radiation patterns before I learned it in school. And what really helped me was seeing it 3-dimensionally. So play around with software like this if you can, particularly if you're struggling to kind of understand things like what a omnidirectional radiation pattern looks like, because I find that it can be really helpful. And then here are some plots. And one of the things that I wanted to mention, because I talked about it in the last class over testing, I talked about cuts of radiation patterns, right? And so I'm mostly used to the polar plots when I was an antenna design engineer. Those are the 3 plots there at the bottom. And so one thing that would be a good idea to get familiar with, particularly if you want to go into antenna design, is to have a good correlation in your head between these kinds of plots here and the 3-dimensional pattern shown, right? You can see that if you slice this through the donut, it's going to be a big circle, right? And sure enough, what does our pattern on the bottom left look like? It's a big circle, right? But you can see if you cut the donut the other ways, it's going to look like that figure 8 pattern that's on the bottom middle and bottom right. This is generally what we expect, even though, like I said, I would not recommend having that large of a gap size for a 15mm length dipole. Next, I want to talk about monopoles. So a monopole, it's just half of a dipole, right? And they are typically almost always mounted above some sort of ground plane. And sometimes the ground plane is just other radials. As you can see here in the photo on the right, this is a quarter wave monopole with ground radials. This was actually the very first antenna design that I ever constructed when I was learning and really had no idea what I was doing. They're typically pretty low in gain, again, that linear polarization, omnidirectional radiation pattern. But these can be pretty easy to construct if you're just getting into it, right? And again, monopoles, it's just a straight, typically vertical antenna, kind of like a rod, right? With the source applied at one end instead of in that middle point of a dipole. And that's the difference there. And monopoles and dipoles are pretty common on their own, but they also have uses with other antennas, right? And I'm going to cover Yagis because I did sort of an extensive build with them a couple of years back, and I know there are a lot of amateur radio operators in the class that like Yagis, and also Yagis are good if you're a student working on any kind of telemetry, student rocket or payload project. If you're doing your ground system antenna and you want something that's kind of cheap but very very high gain. The one thing that I would caution is if you are doing a live launch and a student is in charge of holding the Yagi to receive the telemetry from your rocket, is to mount it so that you can hold it steady without being distracted, right? But with that said, not only are dipoles used not only on their own, but in other antennas, they're used here in Yagis, and that's why I'll talk about them. And technically, this is Yagi Uda array. I think Uda was the grad student to Yagi, so that's why Yagi's name is first, and we all call it Yagi, and poor Uda was forgotten because they were a grad student. That's incorrect. You can just yell at me in the comments. So what are some of the advantages of this? They're high gain, as I said, they have a high front to back ratio. So if you really care about what's happening in front of your antenna, that's where your pattern is going to be. They're also cheap and lightweight. So you can make these out of aluminum rods. You can even have that, and you can have it made out of wood, right? And as far as the high gain, you might see gain antenna contests at certain meetups. I know Microwave Update typically has those, and the winning antenna for 2019 was, I think it was a 14 element Yagi. that Tavis Helm built, and the center boom was wood, right? And he just had the small wires in there for the directors. So if that's something that you're interested in playing with, you know, that's certainly an option. I apologize if I have any of those details wrong. I should have double checked it from the microwave update book before I gave the lecture, but I didn't. So what are some of the cons of this kind of antenna design? For one, if you're going to be doing really high gain, you're going to have more and more directors. So it becomes pretty long, right? And that can be an issue. It only goes up to a certain point with your gain. So it's not going to get you to the same kind of high gain as, say, a parabolic reflector, right? Something that will give you a whole lot. And if you're, this next point really applies for any antenna with a high frequency, but you have to be more and more careful to avoid any measurement or machining errors, the higher frequencies you go, right? And so describing what's going on in this picture on the right, you have the center boom that's going through there in the middle. You have your reflectors in the back. You have your directors in the front, and these help shape your pattern and give you gain. But all of those are parasitic elements. They're not actually driving the wave. What's doing that is your feed element, and you only have one of those. And that's labeled third from the left there. So how do you determine how to make a Yagi for whatever frequency? Well, there are lots of calculators online. One that I have used is this VK5DJ Yagi calculator. It's since been updated since I used it and took these screenshots, but there are a variety of calculators out there. If you have one that you like better, feel free to throw it on the class discussion board. And I'll show how this compares with the actual theory from the antenna theory analysis and design from Baluns. This is when I took, both professors used the same book. So I'll show you how close amateur radio calculator like this matches to the theory that's prescribed in a textbook, right? But when you're using a calculator like this, you're going to input your variables, right? The frequency that you're designing for, this was a 434 megahertz antenna, your diameter of the dipole bend, your dipole gap, whatever coax that you're matching it to, how many directors you want, different things like that, right? And this is the kind of output that you'll get from a calculator like that. Again, this was for a 434 megahertz Yagi. And so this tells you, you know, which director to cut to which length, how far to space it, where it needs to be on your boom, and how much gain it gets you, right? Both in dBd, decibels relative to a dipole, and dBi, decibels relative to an isotropic radiator. And one thing that I do want to caution that I did that made me look silly as a student, so any students, if you are going to use one of these in any of your projects and present over it, notice that these calculators will spit out that you need a 306.8 millimeter length director. Can you measure to 306.8 millimeters? Can you cut to that tolerance, that specifically? So round where you can, don't use unnecessarily precise units that you have no ability to follow through on, right? And this is, you can do some tuning here, and you've got a little bit of leeway, right? Particularly in your parasitic elements. So don't see 306.8 millimeters and think that you absolutely have to prescribe to that. Just get it close. And so I talked about showing the difference between the antenna theory that is taught in a university class versus an amateur radio calculator, right? And here it is. So using one of the tables that was in the antenna theory book, you can see that they range from 296 to 332 millimeters for those first few elements. And the Yagi calculator is pretty close, right? And it gets even closer and more exact the further along the boom, the higher number of directors that you get, right? So you might have to do a little bit of tuning depending on some of the variables that you're considering, but generally they're pretty close to each other. And so what does that look like, right? So you have your big reflector, and this is what I'm going to call the back of the antenna here on the left side of the screen. That's how it's about 35 centimeters long. And then you have 138 millimeters before you get to your driven element, and then 52 millimeters before your next, and then quite a bit longer, right? And they just get smaller and smaller as you go down, and you're radiating down the length of this boom. And that's one of the reasons in my title slide, I talked about wire and traveling wave antennas. You make traveling wave antennas like this out of wire. So it's a wire antenna, but what it does, instead of just being a single wire that is resonant, right, and that just radiates into free space, this is a more of a guided structure that directs the radiation. And we'll see that in the helical antenna as well, right? There's something else going on where it's not just one wire that's resonant, it actually has that guided structure that directs the wave. And that's what's going on here. So I talked about having a half-wave dipole for your Yagi. And so for this example, I did a half-wave folded dipole, right? And so it's the same gain and radiation pattern for a folded dipole as that single wire that we saw in the example. You need to pay attention mostly to the overall length that you're using. And then the next point that you want to be careful about is your diameter, right? And they're less critical for a folded dipole than when you're doing just a straight dipole or the Yagi directors, but it is still important. And the next comment is about that spacing between the arms of, you often call it a trombone when it's in a folded dipole. So it can vary. You can move it around when you're testing and kind of see what the reaction is, but it matters less than that overall length. That's really critical, right? And what's the big difference between a folded dipole and a regular half-wave dipole? The impedance. So we talked about the impedance of a half-wave dipole antenna being approximately 70 ohms. For a folded dipole, it's 4 times that. And there's a derivation that explains why that I didn't include here, but I can link to it if someone's curious. I apologize for not including it. But your input impedance for a half-wave folded dipole is going to be roughly 4 times 70, so 280 ohms. And why is that important? Because we have to match to 280 ohms now, right, instead of 70. So that 70 ohm coax isn't going to solve our problems as easily as it did before. And here's a picture of what I'm talking about. You have your spacing between the wires there, you have your wire diameter, and you're generally going for kind of a soft bend there. And I have a picture of the actual dipole that I used in this project that might be more clear. There it is. And so this is also, how do you make a half-wave dipole and how do you apply a source to it without having your whole boom be receiving that as well, right? Well, you can use plastic keep it above. This can also be wood, anything like that. And you can see I didn't bend it very well here, but you can see on the left side of the screen, the mark where I knew that I wanted it to bend. And you can also see this is the aluminum boom that was used for this project. And you can see in the background, the next parasitic director and how far away that is. So we now have a 280 impedance folded dipole, and we have 70 ohm coax. How do we do that? And I also mentioned before about a dipole being a balanced antenna and a coax being unbalanced. So the way you get around that is by adding in a balun, which is just a hybrid of the phrase balanced to unbalanced, right? And all that is an electrical device that converts between balanced to unbalanced. So, and this can be 1-to-1 if you're going from, say a 70 ohm unbalanced coax to a 70 ohm input balanced half-wave dipole antenna, where you're not stepping up or stepping down anywhere. You're just doing that conversion from balanced to unbalanced line. And they can also be used in the case of this folded dipole for impedance matching, such as 4-to-1. Remember, we talked about from 70 to 280 is a times 4. So we want our balun to step up from 1 to 4. And so that's the half-wave 4-to-1 balun. I have a photo of this on the next slide. So it's used for impedance matching. You can use it for 300 to 75 ohms matching, but also, 250 ohms, anything that's divisible by 4, right? And what is the length of a half-wave 4-to-1 balun? Well, it's about a half-wave, but it's a half-wave times the velocity factor of coax. Whatever coax that you're using. This is going to change depending on what particular coax cable you're using. It's almost always found on the data sheet. If you have just found a roll of coax somewhere and you know nothing about it, that's not going to be helpful. But you can, try to look it up if there's anything printed on the side. But for example, for this calculation, the velocity factor on this particular coax that I was using was 0.85, right? So it's as simple as that. They do make calculators. They make a calculator for this, even though, it does the work for you of converting from frequency to wavelength and inputting your velocity factor if you want to do a double check. But it's really all the calculation is. Gives you the length that you need in feet or inches. So what does that really look like? Well, it's a certain length of coax, and part of it you can see here is soldered to one end, and then you have the outside there soldered to the other end, right? So the center core of that half wavelength piece of cable is what connects the terminals of the dipole. And then the ground shields on the cable, that outer shielding, I think it's often like silver, is all connected together. Now this is just a 4-to-1 half-wave balun. There's a variety available. There's something called a bazooka balun that's just 1-to-1. You can also do a gamma match, is something that can be, you have to do a lot of tuning with the gamma match, but it can be another good way to do that transform and that impedance match. So there are a variety of ones out there that might be suitable for whatever you're doing. Just keep in mind, if you're going from a balanced antenna to an unbalanced line, that you might need one. And also if you're doing a impedance transform. So what does this look like in real life? Here is a photo of a couple of Yagis here. And one thing that I want to point out is that both of these have been weatherproofed. If you are playing around with your antennas and leaving them outside in the weather, you're definitely going to want to insulate any of the RF or electrical connections. And they make they make materials for that. You can use kind of a wrap around your coax, or goop that you can put on everything that won't electrically affect the rest of the antenna. But you really just want to make it so that nothing's going to get in there and corrode. Both of these antennas shown here are only weatherproofed kind of against immediate weather, not for something long-term, because this wasn't going to be a long-term project. And if you look closely, you can see the little loop on the outside of that weatherproofed fed element, and that's the half-wave 4-to-1 balun that we just talked about. And you can also see another Yagi here pointed in an orthogonal direction down the length of the building. And one thing that I want to point out here, because I know a lot of people have similar situations, you might be able to put an antenna where it radiates into free space with nothing around it, right? But look at everything that's around the environment here. Look at all the metal that is around the environment here. That is going to affect your radiation pattern and your signal if you're not careful, and particularly if it's within those zones of the fields, right? So this is not particularly ideal. You want to have it, everyone wants a perfect environment, right? These antennas still worked. I'm just pointing out that you generally have to be careful of other things that are going to reflect and scatter those waves. So what does a really poor version of an HFSS model and simulation look like of a Yagi? Looks like this. You can see kind of just barely that the directors get smaller as you're going along that boom. You can see the kind of directional with side lobe and rear lobe radiation pattern here. And it's hard to see, but you can see that it's not quite resonant at the correct frequency here in the return loss plot. It's a better match at a slightly higher frequency, right? And this was when I was just learning HFSS, so it's probably not a great simulation. One thing that is a small point is generally when you're doing simulations, it's nice to have all your radiation in the positive Z axis instead of along down a line. You'll have people get really fussy about that when you show them professionally the simulations that you do. But it's nice to keep it all in the kind of same template if you're going to be doing that professionally. So what does the built Yagi look like? Here's you can see the 1, 2, 3, 4, 5 directors there in the front, the reflector in the back, and then you can see on the right where that halfway folded dipole is. And again, this doesn't show the balun, right? This is just the built elements. And let's see how bad of a job I did. So what did I not do here? That was the very first thing that I said that you should do. Tuning, right? So you can see the black line there down the middle is at 434 megahertz, which is where my design resonant frequency was. And this is our return loss plot of 3 different Yagis that I built. And you can see they're relatively similar in a lot of the performance here, but you can see they are resonant at slightly different frequencies. I got it pretty close, right? But if I wanted to do a really good job, I would have spent more time tuning and getting that a little bit closer, right, to where they lined up at that 434 megahertz. Now, Does this mean that I couldn't receive a signal or couldn't transmit? No. You can see in that direction, it's all below that 10 dB of return loss that we talked about in last class. That was kind of a good minimum bar to set. But this is what it looks like, even having an HFSS simulation and going through the first Yagi that you might ever build to 3 of them. You can see how they might vary slightly, even though you think you did everything the same. And 2, you can see that they all didn't quite line up where we wanted them to, right? So that's something to keep in mind. And again, why you should tune. And ideally leave enough time, particularly if you have a deadline, that you can take the time to tune your antenna. So remember I talked about Yagis are traveling wave antennas. They have that guided structure to direct the wave. The other kind of traveling wave antenna made out of just simple wire that I want to talk about today is a helix or helical antenna. So these are a really great kind of easy-ish way to get circular polarization, right? And so you can see here in the graphic on the right, you have your central support down the middle, which is going to be what your wire wraps around, right? You have your feed line, typically going to be coaxial cable there at the bottom, kind of similar to how you might excite a monopole, right? It's from one end. You need to have some sort of, insulating support for the helix, so it's not just wire on wire. And directional helical antennas are going to use a reflector ground plane. That's important. And then you just have your wire going around. So there's different types of helical antennas. I'm going to mention the wider variety and then focus on one particular one that I'm most familiar with. So you'll see terms like monofilar. I've only seen it in writing. I haven't talked about it, so I might be pronouncing it incorrectly, but that's where you have just the one helical wire. A quadrifilar helix is going to be 4 wires. That's really common to see, particularly the more advanced that you get. So you can have, 2 or 4 wires going around, just adds in complexity. And as I mentioned on the last slide, if you want this to be directional, it's going to be mounted over a ground plane to really direct that wave. There's 2 general schemes for how your helical antenna might radiate. You have your broadside. So broadside monofilar design. I have not built one of these. They're linearly polarized and it's going to be just parallel to that helical axis. These are what's in, I should have grabbed my handheld, but in like a handheld walkie-talkie, those are often what's inside what looks like that, right? You can also have different versions with more wires. But the one that I'm most familiar with is the end fire orientation that is circularly polarized. And that's going to be coming off the end like this, or shooting it directly like this. And this is frequently used with satellite communication, because again, we talked about space to ground and ground to space signals typically being circularly polarized to allow for that polarization mismatch, right? So you'll frequently see these sometimes as arrays in big reflectors, or you can even have them as smaller antennas and even on spacecraft. So, and one idea that I worked with is how do you get that frame that keeps it exactly off that central axis that we want, that you can rotate it easily. I know a lot of people like 3D printing, and some of the research that I did in undergrad was incorporating 3D printing with antennas, right? And so for helicals, one of the fun things that you can do that's pretty easy is you can 3D print your antenna frame. And I've linked to the specific project that has a really good explanation of how this works with the STP files, and also a link to the calculator that this person used. So you can see here in the back, we've got that coax, and you can see where it's soldered there into our little reflector ground plane, just a little piece of copper. And then we've got our wire that wraps around the supports, and then the radiation comes off circularly polarized from that end. This here shown is S-band right-hand circularly polarized medium-ish gain, 10 dBi. One thing that I will caution when I did this project is that, particularly if you're going to be having a longer helical frame, or if you're trying to be cheap on your infill, the frame can have a tendency to bend, particularly when you're trying to get it off the 3D printer, right? You want to be careful in, making sure it's cool and getting it off of there carefully so that you don't have a wonky frame that then won't fit together. So going through some of the resources here, I have additional explainers on half-wave dipole antennas, and a link to a blog post that talks about the calculation and formula, especially if you're trying to be really precise. Remember, in your 0.96 to 0.98 version percentage of the half wave, and it also depends on your diameter of your wire. I have a link to the Yagi calculator that I used. Again, it's just one that I used that was recommended by my RF lab professor, who is a longtime ham, and I found it pretty easy to work with. The 4-to-1 Balun calculator that I showed, again, it's just half wave times your velocity factor that's from your data sheet on your coax. Another explainer about transmission line balance, particularly for VHF and UHF. VHF and UHF, it's more common to have your Yagis in that range. You can have them on printed circuit boards, right? You can also have them a similar, or sort of similar antenna that is different that I didn't want to go into is a log periodic dipole array. If you're familiar with that, you can also use that in kind of same frequency range. Link to a post about folded dipoles for those Yagis. That was the same resource that I used in university. Link to that 3D printable helical antenna frame and the winding template. You just print off the pieces and then they kind of fit together. It's very clever. In that template, they have a link to a helical antenna design calculator. I've linked to a different one that I thought was a little less intimidating than the one that was used in the Neverse project. In the next class, we'll go over planar antenna design like you would have on circuit boards. So some of the things that we'll cover will be slots, which is an interesting kind of antenna because it's a missing antenna, and patch design. There's a lot of varieties with patches that you can do, and Vivaldis. I know a lot of people that might be familiar with patches. They're very popular for arrays, and again, I won't be going into phased array antennas in this course because that's more of an advanced topic, but I'll kind of give a brief nod to how you would do that with a patch antenna. With that, if there are no other questions, that's all I have. Thank you so much for attending the class. I look forward to seeing you next time, and I'll get more information on that weatherproofing material, the PCB balance, and the nano VNA measurements. But thank you so much.